for the introductions, and let's get started. So in our talk today for cruising in a data lake from zero to scale, we plan on sharing our journey for the data analytics strategy that we employed, and also kind of share the whys, the what, and also the how, and hope to provide some kind of the lessons learned, some of the insights and the techniques that we employed when we try to scale our data lake. So this slide is just kind of an introduction about us. So we are, both Nikita and I are from Here Technologies. Here has been in the industry for 30 plus years. We build location intelligence products, and we also have our own location platform. Needless to say, the amount of data that we collect and mine and process is on a large scale. So this slide is to not only introduce us, but also to provide the premise for why we started to build, how we started to build this data lake, and what were the reasons and what were the challenges. So moving on. So that brings us to the origins of our data lake. So as part of this multiple product suites, we have a high definition map, which is our product suite, which powers self-driving cars. So as part of this, we are providing extremely high fidelity data. So the scale of the data is in petabytes. It has multiple layers which are going on in this product. This map is going to be an insight to the sensors in the car, and it would be used in this ecosystem in order to guide the car to self-drive. So there is a lot of complexities involved in kind of building this pipeline at scale. There are multiple sources, the scale, and also the SLAs which are there in order to provide this as a data as a service. So together, this kind of provides us the origins of our data lake. So where did we start for our challenges for our data lake? So as I mentioned, it's a multi-layer product enriched from petabyte scale data. It's a complex processing pipeline, different cadences of the data, various sources which we process right now. There is predictive training, so we use a lot of AI when we are building this high definition data. So as part of this, we have training model feeds. We are employing a lot of automation via machine learning techniques. And with any kind of algorithm based, we also need human in the loop interactions in order for the fallout handling. So clearly there were a lot of number of different pipelines going on, and that kind of brings us to the lake range. So in this talk, we are going to kind of talk in terms of lake and its data lake. So you will be seeing towards this a theme wherein we are kind of starting off from the origin of where this data lake started to what are the requirements. So lake range is basically our requirements. So we had a lot of processing pipelines which are continuously running. On the right, you can see a complex net of this processing pipelines which are continuously running. These are event-driven pipelines which we run right now, wherein data in from one system goes into the data out of the system. Not all of these pipelines are managed by one team. So we are kind of a distributed team wherein we have a lot of different teams contributing towards the data. So that means that if you want to kind of do any kind of data exploration or do any kind of data-driven insights, it becomes challenging. Either you have to rely on different teams in order to kind of get those data insights or get the data in that form which you desire in order to kind of do the data exploration, or you have to kind of build your own, try to get the data from them and try to kind of build it. So in this complex net, the data also adds. So you have almost terabytes of data getting added. Any organization also has a lot of historical data. So in our case also, we have terabytes of data which gets added. So that also adds to the complexity. So apart from the complexity of the processing pipelines, the scale of the data is also adding to the challenges. And from this, we are generating kind of different insights. We want to generate quality metrics. We want to generate content metrics. We want to generate what's the efficiency of our process, what are our SLAs of our process. So a lot of different data-driven insights can be generated from this. So that is our requirements from where we started. So now that we covered the why and what were our challenges in order to do this kind of data exploration, I wanted to kind of touch base on what is a data lake. So data lake is a centralized repository, and you will find a lot of definitions for data lake when you search on the net. But this is our version of providing what is a data lake. So data lake is essentially, you can store all relational, non-relational data. The basic premise of a data lake is you bring your own first raw data. You do not need to kind of previously, in case of older legacy data warehouses, you had a lot of processing, you had star schema designs, you had to figure out what kind of data you want to mine from this, then accordingly write your ETL jobs, and then get the data in. With the data lake, the paradigm is different. First, you get the raw data in. That can be used for a lot of different exploratory analysis. And then you can also have your staging data in order to prepare the data for analysis. The advantages of doing this, it gives you a lot of different multifaceted use cases which can be generated. So batch reporting, needless to say, everyone loves the BI reports. What a great way to show statistics going through. Exploratory analysis, that becomes really difficult with your traditional data warehouses because there is no clear solution in order to kind of go and query these data. With data lakes, it's very easy possible. Predictive analytics require a lot of kind of training of the data based on history. With data lakes, since you're capturing the historical everything, including the raw data, predictive analytics paradigm becomes much more simpler with the data lake. Machine learning, training models can be trained from this data. We actually do that at scale, leveraging our data lake. The last one, which is the reverse lookup, is not a kind of a quite kind of leveraged use case, but what we do is we use that in order to kind of do secondary lookups on the data. So typically, your main active repositories might be doing primary lookups, but you can use this data sets in order to do reverse lookups, which is essentially you can pivot the data in different forms and kind of use it. So what are the foundation blocks for this data analytics platform? So any data lake or any kind of data analytics platform has a foundation blocks. There are transformers, there's storage, and there's query engine aggregators. Transformers are the ones which are kind of transforming the data. It's the ETL jobs. Storage is where you store it. And query engines are how you query the data, your BI tools. So in terms of that, we started from our mile marker 0 in order to address our needs for our data lake. Data warehouse needs. So we started off with a typical data warehouse. In our company, we had existing data warehouse, which were Redshift. We started to build our own data warehouse on top of it in order to add additional data. Now, the challenge was that you had multiple data warehouses, and now you needed to blend this data across these data warehouses. What that meant was that now the complexity increased. Now you're trying to blend across different data warehouses and try to kind of ensure that they scale. If you wanted some data, as I mentioned, you had long cycle times because you had to rely on some other teams. That's when we decided to consolidate the data in one data warehouse. That's when we had faced the challenges of cluster tuning, wherein you had to put in a lot of kind of effort in order to tune the cluster because your read-write both were going against the single cluster. So your storage and your query engine paradigm was both in the single cluster. And that's where our kind of problems started to rise. We had contentions for read-writes. We tried to kind of tune these clusters, but then we were also accordingly adding a lot of cost. So that's when we decided to rethink and kind of went with our next strategy. So this was our mile marker 0, wherein we started, and I'll hand it over to Nikita in order to kind of provide the next strategy of our data lake that we went to.
So as Sneha just described, we had some issues with the classical setup for data warehousing. So the solution that we went in was some modern techniques. I think a lot of people already know about them. So basically, on the left side, we have our existing storages and pipelines, and we're using Spark to tap into them and read this optimized data that is meant to be consumed by automobiles or by other pipelines into something that is pivoted for humans or reporting use cases, right? And we started, instead of storing it in some Redshift or whatnot, we just utilized Parquet with with S3 buckets, right? So simple. I think one of the big wins is basically just switching to Spark SQL, which is way easier to develop, right? So you don't have to train people as much. No schema maintenance. Obviously, you can just go and delete some columns or do some wild renames, but you can add new columns very easily. Another super important thing that happened is that we separated our readers from our writers, right? And that allowed us to scale these different components independently. So now you can actually go and like you're not hitting the same instance of the Redshift anymore, right? So you don't have to have this single point of congestion. No need to orchestrate any jobs, no competition for resources, and there's little asterisk. So if anyone wants to know more, we can talk about that later. It's easy to share, actually, right? So sharing one bucket with one table is way easier than trying to create some more complex strategies. Doesn't work for everyone, and that's where AWS data lakes will jump in and allow you to do more interesting things. Good compression ratio, right? So if you're using modern formats like Parquet or ORC or something like that, it is actually allows you to even save on your S3 resources. So one of the guidelines and buoys that allow you to navigate this complex environment is that you have to provide uniform interface and uniform data, right? So if I'm a data analyst sitting somewhere in Berlin, I should not go and like set up a special meeting, a special call with some team in Berkeley to find out how they store data, right? I can just know that, oh, okay, we're all using Parquet. Oh, and there's actually a single interface such as Athena or Spark Job, or like basically I know there's a Parquet files on S3, everything that works with that, and there's a lot of components that work with that. It's basically a standard de facto I can use. Frequent incremental updates. Obviously, the data is as good as it's fresh. So at least once a day, we update all our tables, and some of them we update way more frequent, right? And we'll talk about that, how we can do that. One table, one source. This one is not obvious. That you actually, whenever you're producing your tables, you don't want to perform the joins or some heavy enrichments in your ETLs. You actually want to just do it later on and expose as much data as possibly can, and then use materialized views or do it in Athena to make it easier. Consistency and availability first, and it should go as the first, but I really wanted to save it for later. It's really important to have a consistent data set because otherwise it just stops working, right? So as soon as every single time you're trying to produce, like replicate the data and you're getting different results, it just doesn't fly out. And obviously security and compliance, we're a European-based company, GDPR applies to us and hopefully it can apply to everyone, and we have to enforce it as well. So finally, when we started to tap into these different teams and help them out to bring their data to our data lake, or just doing them for them, we identified these standard patterns that there's actually like these 3 types of the tables that we encountered over and over again. And one of them is this log and history, right? So basically the events are popping in and you want to record them and partition them by the date. So let's say you're a bank, you want to track these transactions that are popping in on well, not bank, like a customer on your credit card, and then there's a consistent latest state view, which allows you to see what's the latest state of your data set, right? And then finally, on top of this latest state, you can compute some aggregates and lookups, and also record them in time to see how these things are progressed, right? How much money you spend on the coffee, as a full aggregate day by day, for example, right? So once we identify these things, we actually realize that it actually doesn't matter what kind of data sits inside. You can just apply this cookie cutter template, and it actually looks like our standard relational database, right? So you still have your log, or maybe Kafka or whatever, right? So, and from this log you move to the table. It's called the stream table duality, right? Concept, and just by the ratio of applying the change set to your history or log table and then merging it to the latest state and producing a new version of this table, you can achieve like a lot of things, and then computing the aggregates. So one of the important things there is that when we talked about consistency and availability, this is actually how it jumps in. So we never modify anything that we already wrote. So we're always trying to cook a new version on the side and then switch all the tables to it. Very easy concept to understand. Not everyone does it. All the change that has to be versioned, and can I have next one? And we have to provide this dependency tracking, right? So within a version, you have to understand that this piece of the data that came from this pipeline A that feeds pipeline B is actually correlated with this other piece of the data that produced by pipeline B. So you have to provide this some sort of a dependency tracking between your tables, so people can go and trace this one little piece of the data at very tip of your customer facing product all the way back to the origins and see what went wrong or what went right. So, what are the other like guidelines that are less technical? Well, first of all, you have to know your customers. Can't stress it more how important it is to go and talk to people. And this design actually allows you to track and tailor every single source separately, right? You're not paying for this huge Redshift cluster that everyone sits in. You can actually go and tell you, like, how often do you want your data to be updated? Oh, you want to update it every 15 minutes? Okay, but it will cost that much of money, right? And you can go and talk to people, and I think business appreciates that a lot. So for your fast avenue, you can just go and, again, like deploy either cluster, and there's multiple techniques we'll talk later, and create a lot of these small files that are small Parquet files that are not going to be particularly good, have a good compression ratio, but it will provide this very maybe limited scope with like past 24 hours. So the people actually see what's happening almost online, right? And for like slower avenues, you can buffer these changes longer, right? So accumulate these change sets, and then maybe run once a day or once every 5-6 hours, and that will create this like bigger, fatter Parquet files. So finally, like again, like very simple idea that you can combine both approaches, and you can just deposit these small Parquet files very, very quickly, and allow people to have a look on this or some sort of a view that corresponds with this data that you just recorded, and then once a day or once whatever, you go and you compress and squash all these files into one that has a higher compression ratio. So next slide, please. And there, go back to
Yeah, so I think from this, what we right now, we talked about the foundation of this data analytics platform. You have transformers, we touch base on transformers, we touch based on storage, and then we touch base on query engine aggregators. So this is how it looks like in summary. So the transformers, you can have different data sources. If you have a custom data source, which doesn't fit in your kind of regular paradigm of just plain log files which are coming in through, the data source might be extremely large enough that you cannot go and just push entire raw data in. Then you need to have some kind of a buffer or a throttle or some kind of a base transformation, and that's where you can leverage Apache Spark or any other kind of distributed processing paradigm and get the data in the raw format. The other places of transformations that you can do is you can leverage Glue. Glue is something which is provided by AWS. You can use it directly. It's extremely easy to use. They have their own kind of a console wherein you go and plug and click. It runs the crawler. You provide any unstructured data, and it would create the tables and the raw kind of data for you. So Glue, we have been extremely successful and then kind of having a lot of Glue jobs especially for the more simplistic use cases, wherein you have the raw data in kind of log form and you just want to get the data in, and the data scale is also not that significant enough that you need to throttle it. We also have a lot of event streams within our kind of a paradigm, wherein we have Kinesis streams or Kafka streams. And over there, you can have Lambda events, which you're kind of triggering from there. And from the regular S3 buckets, which the streams are there, they have a time to live. Not all buckets would stay there for a long time. So from that bucket, you can use Glue in order to transition that into your storage. So essentially, you can use event streams. So there are multiple different transformations that you can apply. That's how we did. We had multiple kind of transformations that we applied. In terms of storage, it's raw S3 data in Parquet format, partitioned by date and time. We generate staging data on top of it. You can use drill. There's also materialized views. And you can also, we use AWS data catalog, by which you can figure out there are a lot of different tables and a lot of different buckets. So how do you make sense out of what this data means? So AWS provides extremely handy kind of a tool for discovery, which is called as AWS Data Catalog. And that's what we have been leveraging in order to kind of go and catalog what these tables mean. And at the end, we have these kinds of query engine or aggregators from which you're kind of doing your BI. So we use Athena in order to query our data lake. Tableau has direct connections with Athena. I believe majority of the BI tools provide connections to Athena in order to kind of interact with it. Zeppelin is also a very handy tool for kind of exploration. And you can have your CAN reports. You can have explorations through Zeppelin or Jupyter networks, Jupyter notebooks, sorry. And you can also have Tableau. So this is kind of showing the whole summary of how we built this data lake from these pieces. And last but not the least, how do we operate this whole data lake on an autopilot? Like this we did through our journey wherein we scaled it. Now, how do we let it run through an autopilot without putting in continuous speed boosters? So the key here is abstract the boilerplate abstractions. Nikita walked us through some of the things, like there are distinct design patterns, like you have your historical tracking, or you have your latest and greatest state of data. We have abstracted it as design patterns and provided libraries. Data compression, data partitioning scheme, any kind of these things can be abstracted easily, and that's your boilerplate code that every team who wants to kind of expose their data doesn't have to go through it. So essentially you're creating your own platform, and you're asking teams to kind of integrate and bring their own data in this platform. Needless to say, cost is an important factor. So you do need your eyes onto cost, and then also monitoring. One solution which AWS recently has exposed is AWS Lake Formation. Some of these aspects are also covered by Lake Formation. In our case, we have our own dedicated platform. The reasons being is we had multifaceted use cases, and at that time, Lake Formation just got recently kind of productionized in August, I believe. But in our case, with the custom jobs and also kind of the scale, we have opted for a hybrid wherein we have our own kind of a platform, and in future, we would kind of try to figure out if we can use some aspects of the Lake Formation also. So that's about it. Any questions for us?